All right, so I hope everybody is staying safe and warm with this winter weather that came through last night. As you have undoubtedly heard by now, all of classes were canceled due to the snow, so we are going to have to replace today's lecture with a video lecture. So last week we covered a quick review of what was essentially everything from Physics 1. So we covered what I thought were the most important topics from the first 17 chapters from the book. And in today's lecture, we are going to actually start into electricity and magnetism, which is kind of the core focus of Physics 2. We are going to start with Chapter 18. So Chapter 18 is electric charge and the electric field. So most of Physics 1, we focused on mechanics. So a huge section of Physics 1 was mechanics. Like I mentioned last week, we did do a little bit of excursion into waves with sound, so specifically sound waves. We also talked a bit about thermodynamics and heat transfer, but the vast majority of what we covered in the class was mechanics, or how bodies react when you apply forces to them. In Physics 2, we're primarily going to cover two kind of major topics. We're going to cover electricity and magnetism, which is often combined under one term called electromagnetism. And then we're going to talk about waves. Specifically, we're going to talk about electromagnetic waves. So electricity and magnetism are two related phenomena that are produced by the electromagnetic force. And we're going to start by talking about the most basic kind of electromagnetic force. We're going to talk about electric charge and its associated field, and we're going to talk about how forces act on charges in electric fields. So, as an introduction to this concept, we got a picture here of a child that went down a plastic slide. We've all done it before, where you go down the slide and it makes all your hair kind of stand up and it makes your skin feel all tingly. So what's happening that causes all this to happen? So what's happening is, as this child is going down the slide is stripping away electrons from this child's body. So electrons are being pulled away from this child and they're going to the plastic of the slide, and what that does is that leaves the child with an excess of positive charge on him, and all of those like charges repel each other, and all the like charges in his hair are causing the hair, each individual hair, to try and repel itself away from all the other hairs and make it stand up. So that's kind of a product of static electricity. So let's get into that. Section 18.1 is about static electricity and charge, and we also introduce an important concept called the conservation of charge. So, what is static electricity? Have you ever been walking across a carpet with your socks on, and when you reach out and touch the doorknob, it shoots a spark at your finger? Or sometimes you pull all your clothes out of the dryer and all your clothes are sticking together and you don't understand what's happening. What is kind of relating these two things? So we're familiar with these two experiences, but they're both connected by something called static electricity. So static electricity, like I said, it can cause a spark, it can cause things to want to be pulled together, it can cause things to want to be pushed apart. But what we'll notice, if we're clever, is that all the things in which static electricity are involved are the result of rubbing two objects together. And if we recognize that when we rub two things together, we produce this kind of static electricity, it gives us a hint into what's truly happening. So, static electricity, we are going to explain by something called electric charge. This is a new physical quantity that we haven't talked about before in Physics 1, but we are going to explain it with electric charge. So, static electricity is one of those things that has been studied in great detail by scientists for a long time. And when we talk about Physics 2 with electricity and magnetism, most of the research in the studying of these concepts has happened recently enough in history that we actually know who made discoveries, when they made discoveries, and so we can actually kind of discuss these topics in the context of history for actually when they became, when they were discovered, and when people started figuring out how to use these things to build technologies to improve our lives. Okay? So we have three main characteristics of charge. There are only two types, and we call these two different types of charge positive and negative, and we're going to get into where those names come from later. We know that like charges repel and unlike charges attract. So a positive charge will repel another positive charge, but it will be attracted to a negative charge. Okay, and then the forces between charged particles decreases with distance. So those are kind of the three characteristics of charges that we know, and those were kind of discovered experimentally, if you will. And then, of course, we got a picture here of the famous demonstration where Benjamin Franklin actually flew a kite in a thunderstorm with a key on it, and he was able to see sparks shooting out from this key, and he was able to relate that lightning and static electricity were both the same thing. Okay, so types of charges. How did scientists figure out those three characteristics we just talked about? Okay, so scientists, when they were doing experiments and studying static electricity, they observed that when you rub two things together, they would behave differently. And when they started behaving differently, they called these items were charged. They said they were charged in such a way that they produced forces that other objects did not. So they also discovered that two charged objects would always either do one of two things. They would either attract or they would repel. And they were able to then deduce that there was only two types of charges at work. So I have an example here in the picture where you have a glass rod and a silk cloth. And if you rub a glass rod with a silk cloth, what happens is your glass rod becomes positively charged and your silk cloth becomes negatively charged. So that silk cloth is actually stripping electrons from the atoms of the glass rod. And if you don't understand that, we're going to talk a lot about that here a little bit later. But what's happening is that silk cloth is pulling electrons off of that glass rod, and that glass rod is left with a lack of electrons or an excess of positive charge, and then that silk cloth has an excess of electrons or an excess of negative charge. And if you did that twice and you had two glass rods that were both positively charged, scientists saw that if you hung one from a string and you moved the other one towards that first one, it would cause that one hanging from a string to be repelled from the one that you were moving towards it. Okay, and then they also saw that they could then attract that charge to one of those negatively charged cloths, and they could have that attraction force. And then if you had two of those negatively charged silk cloths and you try and bring them together, they would actually repel each other. So those are the kind of experiments that early scientists that were just discovering these kind of characteristics were able to perform in order to identify the types of charges that were acting in their systems. So, positive and negative charge, we said, were the names for these charges, and the convention actually comes from Ben Franklin. And unfortunately for you and for me and all physics students everywhere, Ben Franklin didn't truly understand how objects were being charged, so he just picked positive and negative kind of arbitrarily. And we will see later that this makes things a lot more complicated or a lot less intuitive than if he had done it the other way around. So what happened was Ben Franklin said, okay, if I rub a glass rod with a silk cloth, I'm going to call that glass rod to be positively charged. He didn't know what exactly was happening, but he called that glass rod positively charged. The same thing, if he took a rubber rod and he rubbed it with fur, he identified that the glass rod and the rubber rod were then attracted to each other, and he said, okay, I'll call the rubber rod negatively charged. He just picked those arbitrarily, and he didn't understand what was happening that was causing these things to be charged. So, what is happening to cause these objects to become charged? Well, to understand what is happening, we have to kind of understand the structure of an atom, right? The structure of an atom. Today, we know that all matter is made up of individual atoms or atoms grouped together to form molecules, but atoms are composed of positively charged and negatively charged particles, and also neutrally charged particles. We'll kind of talk about that. So, atoms contain positively charged particles called protons, and negatively charged particles called electrons, and neutrally charged particles called neutrons. And generally, in its normal state, an atom will have the same number of protons and the same number of electrons. So if you have the same number of positively charged particles as you have negatively charged particles, normally atoms are neutrally charged, or they do not have a charge associated with them. So we have an example over here on the right. I'm showing you an aluminum atom. An aluminum atom has 13 protons and 14 neutrons in its nucleus, the center of the atom, and then it has 13 electrons orbiting that nucleus in orbital shells. And then we can see that we have 13 electrons and 13 protons, so we have the same number of negatively and positively charged particles. So typically, if an aluminum atom is uncharged. Okay, so the amount of charge on an object can be measured. So if we have amount of charge on a object, we can say that if it has more electrons than protons, then it is a charged object, and we can measure how much charge there is, and it has units of coulombs. Okay, Coulomb's is named after the scientist Charles Augustin de Coulomb. He's a French scientist. He lived in the late, 18th century, and he discovered a lot of the relationship between charged particles and then the forces on charged particles. So charge will often depict with the symbol Q, so get used to that. And then 1 coulomb of charge is actually defined based off of electric current. We haven't covered electric current yet, so we are not going to talk about what 1 coulomb of charge means. We will talk about it in later chapters when we discuss current. Okay? So, but I'm giving you a new fundamental, or not, I guess it's not a fundamental quantity, but I'm giving you a new physical quantity called charge and of coulombs, but we really don't have a good gut feeling for how big of something like that is. We typically all know, so everyone's kind of familiar with how long a foot is or how long a meter is. You can kind of have an understanding of what this kind of distance means, but for charge, it's not so easy, and it's not a really clear measure of how much energy something has. There can be a large range of charge that really can mean different things. So for example, to give you a sense of scale, a lightning strike will transfer about approximately order of magnitude 15 coulombs of charge from the ground to the clouds. So lightning is charge moving from the ground to the clouds, and it will transfer 15 coulombs of charge. So we see that, and I just saw that mistake. We'll fix that real quick. So you think about a lightning strike being a lot of charge. But for another piece of information, we can say that a typical cell phone battery, which you may see is 4,500 milliamp hours, over the course of a full charge of that battery, if you run that entire battery from 100% to 0%, it'll actually move 16,200 coulombs before needing to be recharged again. So you think, well, man, that cell phone battery moves a lot more charge than a lightning strike, but a lightning strike is very, very dramatic. And so what you're talking about is power, right? So we're talking about moving charge, which is equivalent to kind of moving energy over an amount of time. So where a lightning strike will move that charge in a very, very short amount of time, we're talking about milliseconds. A 4,500 milliamp hour cell phone battery will move that charge over hours and hours and hours. So the power moved, the energy per unit time is much lower for a cell phone battery than it is for a lightning strike. So let's kind of talk about what we call an elementary charge. So an elementary charge is a new fundamental constant we're going to talk about, and the elementary charge is the amount of charge on a proton or an electron, right? So we're going to say that a proton and an electron both have the same magnitude of charge, but with opposite signs. So the charge on an electron is negative 1.60218 times 10 to the negative 19 coulombs. That is how much charge an electron carries. A proton carries the exact same amount of charge, but it has a positive value. It has a positive value by convention. And then we'll say that neutrons, the other kind of particle in an atom's nucleus, do not carry any charge. They do not carry any charge. So we define what we call the fundamental physical constant, the elementary charge E, and you'll see that a lot written as just the variable E, and we'll say that E is defined to be the magnitude of the charge of a proton, which is defined to be the magnitude of the charge of an electron, which is that 1.602 times 10 to the negative 19 coulombs. So Like we said before, matter is typically neutrally charged, which means that it has the same number of electrons as it has neutrons. And I'll give you another example here. Here we have a neon atom. It shows that it has 10 protons, 10 neutrons, and 10 electrons. So if you wanted to calculate how much charge there is on a neon atom, you would then use your elementary charge in order to do that. So you'd say that the total charge of that atom would then be 10 times the charge of a proton plus 10 times the charge of an electron plus 10 times the charge of a neutron. Well, we know the charge of a proton and we know the charge of an electron, so we can say that the charge of a proton is positive E, so we get 10E. We know the charge of an electron is negative E, so we get minus 10E, and we know the charge of a neutron is 0. So we get 10E minus 10E plus 0 is all equal to 0 because our 10E's cancel out. So if an atom has the same number of electrons as it has protons, it will then be neutrally charged and have a total charge of 0. Okay, so we talk about this. This is not always the case. This is not always the case. We're going to define kind of a new term, which hopefully most of you are familiar with from Chemistry 1. But an ion is an atom or molecule that has a net electric charge. So an ion is not neutrally charged. It has a net electric charge. And we have two different types of ions. We have what we call a cation, which is a positively charged atom or molecule with fewer electrons than it has protons. And we have an anion, which is negatively charged because it has more electrons than it has protons. So we know that opposite charges attract. So a cation and an anion will be attracted to each other, and that's how we form what we call ionic compounds. So I have an example here for sodium fluoride. So sodium fluoride is made up of two different atoms to form a molecule. We have sodium and fluoride. So sodium, as you'll see kind of in the video here, has one electron in its outer shell. So it has one valence electron, and that valence electron is not very well bonded to the sodium nucleus. Whereas fluoride only has 1, 2, 3, 4, 5, 6, 7. It has 7 electrons in its outer shell, and it would rather have 8. It would rather have what we call a full outer shell. So what happens is that fluoride atom then steals that electron from that sodium atom. That makes that sodium atom positively charged, which we call a cation, and it makes that fluoride atom negatively charged, which we call an anion, and then because one is positively charged and one is negatively charged, they are then attracted to each other, and it forms sodium fluoride, which is a salt, but it's an ionic compound. So once those two individual ions come together to form a molecule, the sodium fluoride molecule, another big takeaway is that the total net charge of that molecule now becomes 0, because we have a total of 20 protons between the sodium and the fluoride, and we also have a total of 20 electrons between the sodium and the fluoride. So together, that compound is neutrally charged or has a charge of 0. So if we're saying that all charges are carried by electrons or protons, then the charge on an object must be a multiple of the elementary charge. So for instance, I am made of atoms. So it may be a lot of protons and electrons, but I am made of a discrete integer number of protons and electrons. So you can then say that my total charge would be the sum of the charge of all my protons plus the sum of the charge of all my electrons. So even though that number is very, very large, it is a finite integer number. And then if I'm going to transfer charge-carrying particles from one object to another, I must transfer an integer number of particles. So for instance, if I am transferring 50 electrons from one object to another object, if they're both neutrally charged, when I transfer 50 electrons from the first object to the second object, the first object becomes positively charged, and its charge is an integer a multiplication of the fundamental charge E, right? Because it lost exactly 50 electrons. The same thing, the second object becomes negatively charged, and it has a net charge of 50e, so it has an integer number times the number of electrons, or the number of charge-carrying particles that it gained. So this is called the quantization of charge, which means that charge can only be in discrete values of the fundamental charge. So a natural follow-up question to this is, why is an electron negatively charged? Why is a proton positively charged? And why is a neutron have no charge, right? And the answer to that we can figure out by further decomposing these small particles into even smaller particles, which are called quarks, okay? So an electron itself actually is the smallest particle that it can be. So you cannot decompose an electron into quarks. So you can think about it as an electron is order of magnitude kind of the same size as a quark. We're not actually giving you the mass of the quark, but you can think about it that way. So electrons are much, much smaller in mass than protons and neutrons. And I kind of give you those values there. An electron weighs 9.109 times 10 to the minus 31 kilograms, while a proton and a neutron are both about the same. They're pretty close, but they're 1.67 times 10 to the minus 27. So while those are both very, very small numbers, you can see that a proton and a neutron are about 2,000 times bigger as far as mass. They have about 2,000 times more mass than an electron. Okay, so we can then break protons. Protons and neutrons are bigger than electrons because, unlike electrons, they are composed of what we call quarks. And a quark are very, very, very small particles, and protons have 3 of them, right? So protons are formed by 3 quarks, and each of those quarks has a charge, and a quark is, so the 3 quarks in a proton have charges of a plus 2/3 times the fundamental electric constant, plus 2/3 times the fundamental electric constant, and then a minus 1/3 times the fundamental electric constant. And a lot of times they will call this as spin. They'll call this as spin. So a quark will have a positive spin or a negative spin. So you can see that 2/3 plus 2/3 minus 1/3 equals 1. And so when you sum all those quarks together, you get 1e as the total charge of an electron. Similarly, a neutron is formed by 3 quarks, but this time the charges of those quarks are 2/3 e, and then negative 1/3 e and negative 1/3 e. And you can see when you add all that together, you get 0 e. So the charges in protons and neutrons come from a sum of the charges of their quarks, whereas electrons are not divided into quarks, and they just have the charge that they have. So conservation of charge is kind of builds on the quantization of charge. So if we're saying that charge is transferred between objects through the transfer of electrons or protons, it's essentially always electrons, or almost always electrons, that if I am moving electrons from one object to another, the total number of electrons must be the same. I can move electrons from one object to another object, but the total number of electrons stays the same, so the total charge in a system will always stay the same, right? So therefore we can say that the total amount of charge in any process is consistent. And we have an example here where we're saying that I have initially a rod that has a charge of plus 4e, and then I have a neutrally charged sphere which has a charge of 0. I touch them together. I allow electrons to then flow from the sphere to the positively charged rod. That happens because they're attracted to each other. So the positive charges in the rod are attracted to the negative charges in the sphere. That causes the rod to steal some of the electrons from the sphere, and what happens is I end up with a rod that is charged with positive 2e and a sphere that is charged with positive 2e. So initially, before, I had a total charge between the two bodies of positive 4e, and then afterwards I still have a total net charge between the two bodies of positive 4e, because the electrons have to go somewhere. They don't just disappear. If I'm moving electrons from one body to another, the total number of charged particles in the system remains the same. So let's work an example here. We say a charged object is initially neutrally charged, but it becomes charged by the transfer of electrons. Its final charge is 2.45 times 10 to the negative 6 coulombs. So the question is, did it gain or lose electrons? How many electrons did it gain or lose? So it was initially neutrally charged. We transferred electrons, and then our final charge is 2.45 times 10 to the minus 6. So 2.45 times 10 to the minus 6 is a positive number. So the sphere ended up with a positive charge. That must mean that it lost negative charged particles, which means that it lost electrons. So the answer to our first question must be that it lost electrons, because if it gained electrons, it would have a negative charge. So then, as in accordance with the quantization of charge, how many electrons did it gain or lose? We can say that the number of electrons that it gained or lost in this case would be the charge, its final charge, divided by the charge per electron, right? So I can say that the charge that it must have gained, the number of electrons that it lost times the charge per electron would then be its total charge. I can divide both sides of that equation by the charge of an electron, and I get this equation right here. I get this equation right here. So I can say the number of electrons that it must have lost would be its final charge divided by the charge per electron, and I can determine that it lost a 1.53 times 10 to the 13 electrons. So it lost a bunch of electrons for that 10 to the negative 6 coulombs, because the charge per electron is only 10 to the negative 19 coulombs. So according to the law of conservation, if this sphere lost 1.53 times 10 to the negative 13 electrons, they had to have been transferred to the rod, because those electrons had to go somewhere, so those electrons went to the rod. So now we're going to talk about something I mentioned a little bit earlier and kind of add some clarity to it. So unfortunate sign convention as a result of Ben Franklin just arbitrarily picking the fact that the glass rod with silk was positive. So what Ben Franklin didn't understand is he didn't understand that these charges were happening by the movement of electrons. So when he determined that something was positively charged and negatively charged, and then we were then later able to discover that this was because of electrons moving, the sign convention became that electrons were negative and protons were positive. But in the real world, charge is almost always carried by electrons. Signs is almost always carried by electrons, so it would have been way more convenient if he had made electrons be positively charged. Because we will often in this class, we're going to talk theoretically about the movement of positive charge. So we will talk about what would happen if there was a positive test charge in this situation, and we are going to define a lot of physics equations based off of what would happen to a positive charge. But unfortunately, positive charge doesn't move. So for example, let's look at the picture here. We will often talk about if we have a movement of positive charge. So we take a neutrally charged sphere and we have a positively charged rod, and then we then touch that positively charged rod to that neutrally charged sphere. And we're going to talk about the theoretical movement, or the movement of positive charge. And that excess positive charge in that rod will then spread to the sphere, and then we can almost think about that positive charge as flowing from the rod into the sphere. Now, this is a great intuitive way for us to think about charge as being able to flow between conducting bodies, but unfortunately, that's not what's really happening. What's really happening is because that rod is positively charged, or at least initially positively charged, it actually has a lack of electrons. It has less electrons than it should have to be neutrally charged. So when you touch that neutrally sphere, what's actually happening is electrons are flowing into the rod. So even though we will talk about the theoretical flow of positive charge from the rod into the sphere, what's actually happening is electrons, which are negatively charged, are moving in the opposite direction. So this is extremely confusing, especially when we start talking about electric current, but we will get to that in later chapters. So that was all of 18.1. Let's get into 18.2. So we had a little bit of actual equations and numerical theory in 18.1. Almost all of 18.2 is going to be some definitions, and then we're going to talk about why materials act certain way. So we're going to define kind of 3 different types of materials in this section. We're going to talk about conductors, insulators, and semiconductors. So the first one we're going to talk about are conductors. So some substances allow charge to flow easily through them. And examples would be, you're most familiar with, are going to be metals, but it also includes things like salt solutions in water or any ionic bonded solution in water. These are 2 examples of materials that allow charge to flow through them easily. But why does that happen? Well, that happens because in metals, electrons, specifically the valence electrons, electrons that are in the outer shells of those atoms, they're very, very weakly bonded to the nucleus. So when metals form them, or they form a solid, all of those atoms arrange themselves regularly, but all of the electrons in their outer shells are only weakly bonded to the nucleus of those, and so those electrons are then kind of free to move about between those atoms. So we have all of these charge carriers which can freely move through the solid metal, and that allows metals to carry charge or move charge very easily. In salt water, an ion like sodium chloride, it's formed very similar to sodium fluoride, which we showed already, but the ions actually dissociate in the liquid water. That means they break apart. So in water, you have sodium chloride dissolves, and then you have a bunch of sodium ions and a bunch of chloride ions, which are both charge-carrying particles, which are able to freely move through the liquid, right? They're able to move around. They're just kind of free about in the liquid, and they can carry charge through that liquid very easily. So these kind of substances, which can allow charge to move easily through them, we call conductors. We call these conductors. So metallic conductors was kind of the first one we talked about. So like I said before, metal atoms arrange themselves regularly into what they call a crystal lattice structure. So here is kind of an example of one type of metallic crystal lattice structure on the bottom right side of the screen. You can see that they form this kind of 3-dimensional regular pattern, but all the valence electrons, the outermost shell electrons in those metals are kind of free and independent, and they can just flow through that structure very easily, and that means they can carry charge easily through that metal. So examples would be of a good conductor would be something like copper, right? So copper is a metal. It's what all the wiring in our houses use. We know it's good at carrying electricity because we see it used for that all the time. Well, copper has 29 protons and 29 electrons, but the most important thing that we recognize here is that copper only has 1 valence electron. It only has 1 electron in its outer shell, so that 1 electron is not very well bonded to the nucleus, and it's easy to move around through that structure, right? So valence electrons, so that is why metals are generally good conductors, is they have a few number of valence electrons. A lot of times you'll hear this concept called the sea of electrons. The sea of electrons, like a sea that you would sail through. It's an indication these electrons kind of behave. You can approximate their behavior like a liquid. You can approximate that these electrons can flow through through the metal like a liquid. Okay, the other type of we talked about conductors, which are items that are materials that allow charge to pass easily through them. The other side of that coin would be something called an insulator, right? Other substances, such as glass and rubber, they don't let charge move through them very easily, right? And we call those an insulator. In insulators, electrons and ions they're bound to their structure. So in insulators, you have full outer shells of your electrons, or your electrons are bound very tightly to your nucleus, so it's very difficult for those electrons to move and then carry current through that material, right? And that's why we use things such as rubber or plastic to coat the outside of wires. So the wire would be the copper inside allows current to flow through it easy, but the sheathing on the outside of that wire does not allow current to flow through it, so that you can have current flowing through all those wires, but charge can't jump between the wires, right? It's all confined by that sheathing, and it can't jump from wire to wire. So Let's say we have some examples here. So charge can move as slow as 10 to the 23 times more slowly through an insulator as compared to a conductor. Now notice that I said that insulators resist the flow of charge. They don't completely stop it, but 10 to the 23 is a really big number. So in many cases, we can approximate an insulator as having absolutely no charge moving through it. And then we have some examples. So pure water, which does not have any salt dissolved into it, doesn't have any free ions in that water to conduct charge or to move charge. So pure water or distilled water is not a good conductor. It is in fact an insulator. And dry table salt is in fact an insulator because we said those sodium chloride ions are still together, right? They're still together, and the net charge of a sodium chloride molecule is 0 because they add together to the cation and the anion are together and with a net charge of 0. But as soon as we put that salt into water and those ions dissociate, now we have freely moving charged particles, and salt water becomes a conductor. And the same sort of thing happens when you melt table salt. So it melts at a very, very high temperature. But if you were to melt table salt, it actually causes some of those ions to dissociate, and molten salt is actually a good conductor as well. So the best insulators, like we said, have strong bonds between the nucleus and their electrons. So that typically means that you're going to have a full shell of your outer electrons. Your valence shell is going to be full, right? And then we can also say that most insulators are typically not atomic or elemental material. So they're not things like copper or aluminum or gold, which are only made of a single type of atom. Insulators are typically molecular, which means they have multiple different types of atoms bonded together, because when atoms bond together, they typically do so in such a way that they fill all the outer shells, right? They fill all the outer shells, and so now you have electrons that are shared in between atoms, and when you share those electrons in between atoms, those electrons are locked in place. They are locked in between those two atoms, and they are not free to move about the structure like they are in like an elemental metal like copper or aluminum. The last type of material we're going to talk about are called semiconductors. So semiconductors, as you'd probably imagine, are somewhere in between a conductor and an insulator, right? They're somewhere in between a conductor and an insulator. They have a lot more in common with metals than they do with insulators in the fact that they typically form well-ordered structures. They typically form that same sort of crystal lattice, but they have more valence electrons than a metal. So a metal like copper only has 1 valence electron. A semiconductor may have 4 valence electrons in its outer shell. So they still kind of form some bonds with their neighboring atoms, but they do have some amount of electrons in their outer shell, which are a little bit more weakly bonded. So some charge can flow, some of it may not be flow. So they act as something like in between a conductor and an insulator. Now, the important thing about semiconductors is that they can be controlled, and this is why they are so important for use in electronics, right? So what you can do to a semiconductor is you can add what you call impurities through a process called doping. So what I can do, and for instance, the example I'm giving is silicon is a really widely used semiconductor, and it has a known ability to move charge. But I can add other elements that are able to change the material properties of that semiconductor to allow it to move charge more easily. So a big type that they use antimony a lot. And if you add an antimony atom into the crystal lattice of silicon, it actually adds a free electron. It adds a free electron because antimony has 5 electrons in its outer shell, and so when you add it to silicon, which has 4 electrons in its outer shell, you end up with 1 extra electron. And so you have this 1 extra electron, which can act as a charge-carrying particle to allow charge to then move through that semiconductor. So the more antimony I add into the semiconductor, the easier that charge moves through that semiconductor. And people, they can control very precisely how many or what percentage of antimony is added into the semiconductor. So they call that a dopant atom, and they will have concentrations that are very, very precisely controlled, and it may be anywhere from one antimony atom to 10 to the 4, so 10,000, one dopant atom per 10,000 base atoms, all the way up to 10 to the 8, which is, let's see, not quite a billion, so 100 million. So it may be one dopant atom per 100 million. So the higher the concentration, so if it's one dopant atom per 10,000, it's going to allow charge to move a lot easier. If it's one dopant atom per 100 million, it's going to have charges move much slower. And how they add that concentration, they can precisely control how easily charge moves for a semiconductor, which has a lot of application in modern electronics. So there are several different ways. This is kind of changing gears, but it kind of falls next in line with how we talk about transferring charge. There are different ways to charge objects, right? There are different ways to charge objects, and we're going to talk about two of them. The first one is going to be charging by contact, which is the simplest and kind of the most intuitive to understand. So what I can say is if I have two conductors, one is negatively charged. If I bring that negatively charged conductor into contact with another conductor, that negatively charged conductor has an excess of electrons, and when it touches that other conductor allows charge to move easily through it. That means that electrons can easily flow from the first object into the second object, and by touching that second object, I end up charging that second object negatively charged as well, because I have transferred electrons from the first object to the second object. So this is kind of the easiest idea for how you can charge a conductor. The other way that we can charge, we call this charging by induction, and this is not quite as easy to understand, but we'll kind of walk through an example of how to do it. So charging by induction, I can charge two objects by not directly contacting those two objects. So how we're going to talk about doing that is we're going to talk about, consider kind of the picture the way we have it shown. Let's say we have two conducting spheres that are touching each other. They're touching each other, and initially they are neutrally charged, means they have no excess charge on them. And now, while they're touching each other, I bring in a positively charged object close, but I don't allow it to touch the spheres. So we say that like charges repel and unlike charges attract. So that positively charged rod will attract a bunch of electrons over to that side. It'll attract a bunch of negative charged particles over to that side, and it will leave the other side, the other sphere, with a net positive charge. So what's happened is the sphere on the left is getting a bunch of electrons from the sphere on the right because they're all attracted to the positively charged rod. Both the spheres are conductors, which means that charge can freely move between the two as long as they're in contact. Then what I can do, as soon as I have a net charge on one sphere, I can then separate those spheres. I've never touched them with the rod, but I can now separate the spheres, and then I can take the rod away. And what happens is that left sphere still has an excess of electrons, but now it's no longer touching that sphere on the right, so now I can't allow the electrons cannot flow across that air gap in order to equalize the charge, and I end up with a net charge on each sphere. So I end up with a sphere that is negatively charged and a sphere that is positively charged, and that is called charging by induction. So there's one more thing that we can kind of talk about, and that is called induced polarization. And induced polarization, we're typically talking about insulators. We're talking about insulators, or things that do not allow charge to move easily through them. So what we can do here for an insulator, insulators can all kind of become charged just because they're made up of atoms, not because that charge can move through them, but all of the individual atoms can be polarized. So in this example, let's say I have a positively charged rod, and I'm bringing it down close to these paper circles, from a hole punch that have been cut out. So Paper is an insulator. It doesn't allow charge to move through it easily, but paper is made up of atoms. Paper is made up of atoms. So all of the atoms that make up that paper, then when they see that positively charged rod coming to them, they say all the electrons from all of the atoms all get kind of sucked to one side of the atom, and so every single atom becomes polarized. That means it has a negative charge on one side and a positive charge on the other. And then what that means is I end up with a net negative charge on the one side of the paper that's closest to the rod, right? It's closest to the rod. So that you can say that for insulators, it doesn't matter if my rod is positively charged or negatively charged, but you can actually attract yourself or be attracted to an insulator just through the polarization of the atoms that make that insulator up. Okay, so 18.3 is Coulomb's law, where we talk about the force between charged particles. So earlier in the chapter, we introduced Coulomb, who was a scientist who has the unit for charge named after him. One of his biggest additions to science was he kind of discovered the relationship between how charged particles, or the magnitude of the forces that acts between charged particles. So we said we had 3 observations about charges. We said there were 2 types of charge. We said like charges repel and unlike charges attract. And we said the force between charges decreases with distance. So scientists did a bunch of experiments, and they were able to refine these observations into one mathematical formula, which we call Coulomb's law for electrostatic force. So electrostatic force is going to give us the magnitude of the force between 2 charges. And that law is given to be that the electrostatic force is equal to K times Q1 times Q2, all divided by R squared. So force, we said, was the electrostatic force, which is either going to be the attraction or the repulsion between 2 particles. K is known as the Coulomb constant, which is 8.988 times 10 to the 9, and it has units of newtons meter squared per Coulomb squared. And Q1 and Q2 are the charges of 2-point charges, Q1 and Q2, or the magnitude of the charges of 2-point charges, and R is going to be the distance between those 2 charges. Okay, so that's the magnitude of the electrostatic force, and what we have to recognize then is we have to then apply the like charges repel, unlike charges attract ourselves in order to understand the direction of the forces. So for example here, I have the top picture shows Q1 and Q2, where Q1 and Q2 are both positive. So we can then say that the forces repel. So if I say F1, and F1 is going to be the force on Q1 by Q2 is going to be to the left or away from Q2. Similarly, F2, which is the force on Q2 due to Q1, is going to be to the right because they repel. Or the opposite scenario right below that, in which Q1 is positive and Q2 is negative, the forces then are towards each other. So the applied force would then point towards the other particle, and we would have to do our math based off of the direction that the force would be applied. We have to determine that based off of the sign of the charges. So let's do an example. The repulsive force between 2 identical charges separated by 1 centimeter is equal to 90 newtons. What is the magnitude of the 2 charges? So I'm saying I have 2 charges, Q1 and Q2, and I gave you the fact that they're identical. And then I also say that the separation between the 2 is 1 centimeter, and then we have a electrostatic force of 90 newtons. So I give you a good diagram here. The force on Q1 due to Q2 is 90 newtons to the left or away from Q2. Whereas the force on Q2 due to Q1 is to the right or away from Q1. So we just use Coulomb's law for electrostatic force. We say that F is equal to K Q1 Q2 over R squared, but I gave you that the magnitude of the charges are identical, so that simplifies to K Q squared over R squared. Now I can just solve this equation using some basic algebra for Q. I get the square root of FR squared over K. I know everything in that equation. I know F is 90. I know R is 0.01 or 1 centimeter, so 0.01 meters. And I know that K is 8.99 times 10 to the 9 newtons per meter squared per Coulomb. So Big takeaways from this is you have to recognize that our K, which is our Coulomb constant, is in our base units. It's in our base units of Newton, meter, and Coulomb, so we have to convert everything back to our base units so that it all matches with our constant. So we have to convert from centimeters to meters. Now I just plug all that into my calculator, and I can determine that Q is equal to 1.00 times 10 to the negative 6. So that's asking what is the magnitude of the two charges. That would be the answer. It's 1.00 times 10 to the negative 6, or 1.0 microcoulombs. But there are two possible choices. Either both charges are positive or both charges are negative. Like I said, the question specifically asked for the magnitude, so your answer would just be 1 microcoulomb. Okay, so let's do another example. So we have two neutrally charged bodies are separated by 1 centimeter. Electrons are removed from one body and placed on the second body until a force of 1 times 10 to the minus 6 newtons is generated between them. How many electrons were transferred between the bodies? Okay, so let's think about this for a second before we jump into the solution. So we can say that we transferred electrons from one body to the other body. So if I transfer electrons from one body, it's going to end up with a net positive charge because it's losing electrons. The other body is going to end up with a net negative charge because it's gaining electrons. So they're going to have opposite charges at the end. So I know that the forces will be towards each other. They will be an attractive force. Okay? Now that's kind of a good concept for us to think about. Now let's kind of figure out how we can solve this problem. Once again, we use Coulomb's law for electrostatic force. They gave us the magnitude of the force this time. And this time they said that the magnitude of the force is 1 times 10 to the minus 6 newtons. So I can then solve this equation. I can say that if I move a discrete number of electrons from one body to the other body, if they're both initially neutrally charged, they will have the same magnitude of charge at the end. One will be negative, one will be positive, but the magnitude of that charge will be the same because they're taking the same number of electrons from one and it's gaining that same number of electrons on the other. So they'll end up with the same charge. So I can say once again that my force, my Coulomb's law force, is Fq squared over r squared. I know what F is. I know what K, it's a constant. Once again, I gave you that the distance was 1 centimeter or 0.01 meter. I can now solve for Q squared, and I get that Q is equal to 1.055 times 10 to the minus 10 coulombs. So I know what the charge needs to be on the bodies. So now that I know what the charge needs to be, I can then say that due to quantization of charge, I must move a certain number of electrons in order to gain that charge. So the charge is caused by gaining or losing electrons. Once again, we can say that the number of electrons is going to be equal to the charge divided by the fundamental charge, or the fundamental electric charge. Okay, I apologize about that. I had an error on the slide. This number is correct. This number was incorrect. This number is now, it didn't change. It was always correct. But I can say that since my net charge, which I found to be 1.055 times 10 to the minus 10, I can divide that by the elementary charge, which is 1.602 times 10 to the 19. And I discovered that we had to transfer 6.58 times 10 to the 8 electrons. So that means that one body lost 6.58 one body lost 6.58 times 10 to the 8 electrons, giving it a net charge of a positive 1.055 times 10 to the minus 10 coulombs. The opposite is true of the other body. It gained 6.58 times 10 to the 8 electrons, giving it a net charge of negative 1.055 times 10 to the minus 10 coulombs. So when we talk about contact forces, you'll often hear people kind of quote from Physics 2 that nothing actually touches anything else. So when we talk about physical contact, or forces that are between an object that's touching another, so if I have my hand here and I apply a force from this one hand to the other, all physical contact forces are actually a result of Coulomb's force. And what's actually happening on the microscopic scale, when two objects get super close to each other, all of the electrons in the outer shell on the surface of my hand meet all the electrons on the outer shell of the surface of this hand, and they repel each other. So as my hands get really close together, this R squared in the bottom of Coulomb's electrostatic force law gets really, really small. And as that number gets really, really small, the electrostatic force gets really, really big. So in real life, nothing ever truly touches anything. It's all of the electrons are being repelled by the other electrons. So all the electrons in the atoms on the tips of my fingers are meeting all the electrons in the palm of my hand, and they're repelling each other, and that is how my physical contact force is transferred from my hand to my palm, or from my finger to my palm. So the electrostatic force from Coulomb's law is in fact a vector force. So we can say that the force is either attractive or repulsive, and we then have to use the geometry of the problem to determine the direction of that force. So Coulomb's law gives us the magnitude of that force, and then we have to use the geometry of the problem to determine the direction of the force. So we know that same sign charges will repel and opposite sign charges will attract, and then we can say that the vector will either point towards the other charge or away from the other charge. So let's work an example. I can say two charges and the relative position are given below. What is the magnitude and the direction of the Coulomb force on Q1 due to Q2? So let's take a look at this problem. I have Q1, which is 12.2 times 10 to the negative 5 coulombs, and I have Q2, which is negative 3.10 times 10 to the minus 5 coulombs as well. Now I can see they're separated through an x distance of 15.2 meters, and then they're separated by a y distance of 4.68 meters. So immediately what I do, and I see this kind of problem, is I step back and I look, and I say, okay, Q1 is positive, Q2 is negative. That means that they are attractive to each other. There's an attractive force, so I know that the direction of the Coulomb force on Q1 due to Q2, so that's the force on Q1 due to Q2, will point from Q1 to Q2. So I know that right away. Now let's actually do the math and try and figure this kind of thing out. So we can say that Coulomb's law says that the magnitude of the force is kq1 q2 over r squared. I can then plug all my values in, so I know that r, I need the r to be the distance between my two charges. Well, I don't know that distance from the problem, but I can figure it out because the distance between them is just the hypotenuse of a right triangle. So I can say the distance between them is 15.2 squared plus 4.68 squared, square root of that whole thing. So I get the distance between those two particles is 15.90 meters. I can then say that my force then is 8.99 times 10 to the 9, which is my Coulomb constant, times my Q1, which is 12.2 times 10 to the minus 5, times my Q2, which is 3.10 times 10 to the minus 5, all divided by my r squared, which is 15.90 squared. I solve for that, and I get a magnitude of my force as 0.134 newtons. 0.134 newtons. So I can say that opposite sign charges attract, so my force on 1 due to 2 points from Q1 to 2. So my force will then align with this r vector. It'll point from here towards here, which means that it has the same direction as this vector. So I can then say that the tan inverse of 4.68 over 15.2 is 17.1 degrees. So I know that the magnitude of my force is 0.134 newtons, and I know that its direction is to the right and up at 17 degrees above the x-axis. So I can now know, I can define the full vector of this force because I have both the magnitude and the direction. So that is going to be where we stop for today. So that is the first part of chapter 18. Be prepared to cover the second half of chapter 18 on Thursday.